Today we're going to be discussing Physics Lab02, Projectile Motion, for Physics 2211. The main objective of this lab is to understand how objects translate in space based on the forces that act upon them. Okay, so on the right you can see our tracker setup. We have a center of mass and then use the track feature to get its position in space over time, and you're just going to kind of click the center of mass as you see it frame by frame, and then make sure to also set up your coordinate axes and a reference. So on the bottom you can see that blue line that's indicating a meter stick, so that the track can just sort of figure out like how far apart things are. On the left you can see our important formulas. We have the position update formula. We use this with our position coordinates to get an initial velocity, and then you also have our forces. We have our force of drag and force of gravity. These are going to be the things that are acting upon our ball in space, and then our F net, which is important just sort of generally for figuring out changes in velocity. Okay, initial conditions. So I used the first 2 points in the experiment, like I said, with the position update to find our initial velocity. I then inputted that into the tracker setup, and then to find B, which is our constant for the drag force, I looked at instantaneous accelerations divided by instantaneous velocities proportional to mass. So that's going to give you the B, and you can see it's very small. It's probably because we have a very small mass, so it shouldn't really have a huge effect. Moving on to the results portion of the lab, our first setup without air resistance being accounted for is on the left, and our experimental data is on the right. As you can see, it mirrors it pretty well. Maybe you can see that the experimental is going to level off in terms of velocity, the slope a bit faster, but this is just due to small forces in air resistance, and honestly, slight errors might sort of obscure this idea. This is our second setup. As you can see, the results are very similar. The air resistance on this crumpled up piece of paper is not going to be huge. It's not going to have a massive effect. If we were dropping something far less aerodynamic, like a flat piece of paper, then not accounting for air resistance might have skewed the results a lot more. But in this case, it doesn't have a massive result. So our system is the ball, and the surroundings are the earth and air, which are the 2 things that are sort of doing are exerting forces on our system. And then causes for error, we might have issues because the tracking is blurry and the positions of the ball might be a bit inaccurate due to the frames per second. The velocity initial is approximated, and so is B, using experimental data, and we aren't using calculus to calculate these amounts. We're sort of using crude changes in our position and velocity data. You can see a small code snippet that just shows the second setup where we account for both of our forces, both gravity and air resistance. Okay, for our what ifs, what if terminal velocity is something that happens when falling objects experience 0 net force, is because the force of air resistance grows to be the same as the gravitational force. In this case, this is not going to happen because this ball has not been falling nearly long enough for it to reach terminal velocity, and you can even see that the magnitude of the velocity is still increasing. It's not logistic, and it's not sort of leveling off asymptotically. So that indicates that the force of gravity actually is greater than the force of air resistance in this case. We could have designed our experiment with terminal velocity in mind by using maybe a flat sheet of paper or tracking the position of the object over a longer period of time. All right, the second what if, imagine the object were initially thrown straight up with the same initial speed as in your experiment. Would the time it takes it to reach the ground be the same, longer, or shorter than it took in the original experiment? So because we had forward velocity, basically if you took all of that forward velocity, that's the magnitude of our velocity, which is our speed, and directed it directly upwards, then obviously it's going to travel upwards for a longer period of time, and then it's going to take longer to fall on the ground. Sort of intuitively what you'd think would happen. Okay, thank you for watching.